Our third speaker this morning, Central Time, is Jan Coleman, partner at McKinsey and Company. So Jan, if you can, okay, we can see you now. Thank you. We can hear you too. So so let me share some details about Jan. Jan is joining us from Amsterdam to share how McKinsey has applied PPM to address specific challenges during engineering. Jan actually holds a Master of Science in Aerospace Engineering, more specifically in Design and Production Composite Materials from Delft University, and an MBA from INSEAD, a very prestigious program around the world. He's also a member of the European Construction Institute's Project Delivery Direction Group, and a member, of PPI Industry Council. So, Jan, welcome to the 2020 Annual Symposium, and thanks for being here with us today. Please proceed to share your screen, and the control is yours from this point forward. I will confirm once we are able to see your content.
Fantastic. Thank you, Roberto, for the warm introduction. I'm hoping you can see this.
Let's wait a few seconds.
I'll make sure I go to this, and we'll go there. Is it coming through?
Yes. The stage is yours. Thank you.
Fantastic. All right. Thank you again, Roberto, for the warm welcome. Greetings to all those taking the time to join us today, wherever you may be in the world. Like Pagdira, I hope that you and your loved ones are safe and healthy in what sadly are challenging times. It's an honor to be able to share with you today at the 7th PPI conference. Maybe before I start, a small note on McKinsey, because you might be wondering what we're doing here, as we're typically known as a strategy consultant. And what I just wanted to clarify is that we actually do a large part of our work in helping clients transform their operations, which includes their capital projects. And as part of this, we have a vibrant group of colleagues like myself who are passionate about helping clients improve the development and delivery of their capital projects. My personal role at McKinsey, so I'm a partner in this capital excellence practice, has been really to drive excellence in the engineering and execution of major projects, and really trying to find what are best practices and ways to improve the business outcomes of major projects. So specifically cost, schedule, and cash, much like Gary was saying in the beginning. In this effort, I've had the privilege, and I truly see it as a privilege, to having been introduced to SPS and PPI, as this was for me, really an eye-opener into what level of control and structural and continuous improvement is possible through PPM. And as Roberto was saying, today I'll share one example of how PPM helped a specific project accelerate the delivery of the engineering phase of this project. I can't share who the client was, as we have strict confidentiality that we have to honor. But just so you understand the setting, in this case, we were serving the EPC on a production system optimization effort for their engineering phase, and I'll get into it in a minute. So, what was and what I'll try and share with you kind of the story or the case example, right, to bring it to life for you what we did. So, as I was saying, this is an advanced industries client. So an EPC specializing in projects that consisted of putting specialized equipment in a set of different locations. Okay, so think towers, radars, those types of equipment that had to be engineered to specific site locations. Okay, so this project consisted of delivering several of these design types at over 30 locations. Okay, so that was the scope of the project. It was a multi-year project, several hundred millions of euros in value. What was the situation? So the engineering scope, they had decided to break up the engineering phase and the construction phase in two distinct parts, where engineering was being run as kind of a factory, and then, or at least they wanted to produce the completed engineering design such that they were on stock for the construction team to put in place. That was the setting that how they were thinking about it. But the engineering scope was critical to unlock long lead procurement activities. Now, what was going on when we started to help them was that they'd been working on this for about a year and a half. They'd run into significant schedule delays. They had just rebaselined the schedule 4 months prior to us getting involved. And even after that rebaselining of the schedule, they were still suffering from schedule slip. When we engaged them, they were describing that both the regulatory environment was challenging, the design inputs that were coming from different stakeholders was complicating things. There was low clarity on the overall engineering process, and it really was challenging to deliver both on the customer requirements and the schedule. That was a bit the context. So this was a project in the engineering phase, struggling to maintain schedule. So the approach we took, we leveraged, we used or deployed product production management, and I'm sure you've now seen, that consists of two major parts. You have the production system optimization part, and you have the product production control part. And this was really an example of the first, the production system optimization. And it consisted of 3 steps. We mapped the standard engineering process, because as I was describing, they had to develop 3 designs across 30 locations. So therefore, each design type, we could map the standard engineering process needed for that design type. And we could do that for design type 1, 2, and 3. Once we'd done that mapping, we modeled the way the production system would work if we understood the production parameters and the characteristics of that production system. So we modeled it to see how long it would take to produce the 30 design types of each. 30 units of each design type. And then we looked at how do we now optimize this production system such that we accelerate the completion of these units and therefore the overall schedule. After understanding that, we then went on to deploy product production control. That was what we want to do. Let me just talk through this approach. So what were we confronted with by the engineering team? Okay, so now we're moving away from the client context to actually the specific project team and the pain points that they had. When we started engaging with this team, we found that the engineering team said that the tasks that they needed to do to complete engineering were either not fully defined, were not aligned, as in who was doing it, or what were the handoffs, or in some cases we even found that tasks were not even known. We also saw that there was a siloed approach. So we saw that there was too infrequent or inefficient interaction and alignment between individuals and subteams. There was a fragmentation of resources. So we saw critical people that were required for a specific step in that engineering process having to choose themselves how to optimize their time allocation between different tasks and different design types. We also heard from the team that they had zero early warning or visibility on risk of delays, right? So they were always being surprised by further delays. We also saw a strong focus on excuses. It wasn't me, it was because of this, something went wrong, we should have done this different 2 years ago, etc., right? And not really a ability to address the root causes for delays when looking at individual task execution. And we also saw a buildup of work in process, i.e. designs getting started and deliverables taking longer and longer and longer. So this was the challenges experienced by the product team, and to be honest, these are challenges that I have come across more often in very different parts of a project lifecycle. This really happens more often. So what did we do? We started with detailed production mapping, right, to set the stage. And maybe to clarify what we did. So what you see here is a representation of a standard engineering process for one design type, okay? And each of the boxes is an operation. So what type of operation might you have? For example, drafting a high-level design doc, or obtaining a quote or statement needed for a site surveying so that they get the input for the design, or producing a certain specific detailed design doc, or reviewing updated requirements. Those are types of operations that were part of this standard engineering process for a design type. And each row was a team, and I'll get back to that in a minute. So what did the production mapping capture? So the production mapping captured what are the activity sequences and the handoffs inside this production system. We also got what is the workload and the level of effort needed for each of the operations. So how much does it take in terms of man hours a specific individual to do a task? And then we looked at what are the capacity constraints when we're looking across all the members of a team and therefore the capacity of the total system. Then we also understood other variables like what was the typical variability when executing a task. So again, we would try and understand when we draft a high-level design doc, how long does that take a team member to actually do? So with that, that's the information that we tried to capture with the production mapping. Now the interesting thing was that step alone was already considered as extremely valuable by the project team itself. Right? You can see some quotes on the right-hand side. Right? We had engineers expressing that the exercise was extremely helpful in defining the required work to deliver. Mind you, this was after a year and a half that they were already working, right? A breath of fresh air to understand what we actually need to get done, right? So again, in the PPM framework, this really clarified how they actually were able to deliver their work. What we then did from a production system optimization perspective, this was a static analysis. So what we looked at is where would we expect the bottlenecks to emerge in the production system of each of the design types. So we looked at what is the peak throughput, which is the dotted line, the number of designs that we needed to get through in a particular period of time to meet the schedule need, right? So the schedule determines the demand. That we translated into peak throughput need. And then we looked at if we understand how much work it takes, right, and how much capacity it takes to produce a unit by a team for each operation, we could already do a static analysis and understand where the likely bottlenecks were. So that's what we did here. Yeah, and what we could see was that in all cases, so design type 1, 2, and 3, we had bottlenecks, which meant that there was no way we would meet the needed peak throughput, right? So we knew that we were in trouble already just from that analysis. What we also saw was that design type 1 was constrained by the capacity of team 2, and therefore that was the peak number of units that they could produce. Similarly, design type 2 was constrained by team 3 and 4. Design type 3, the throughput was constrained by team 1. So we were much better able to understand which teams were likely to be the bottlenecks that we had to address. What we also saw is that team 7 had structural shortage of capacity across all 3 design types. So again, we could start to figure out what do we need to do in terms of capacity in our different teams, yeah, to start doing that. And just so you're clear what the teams were, so for example, one team had to engineer the solution, so the design type, I should say, one team had to engineer the design type, so the equipment. One team had to do the specific site design, so making sure that the electrical and the foundations and all that was in order for that site. There was one team that was looking at safety needs. There was one team looking at supply chain, etc. So those were the types of teams having to do operations in that production system. We then said, we then said, okay, this is a static analysis, but given that this is grounded in operations science, we can actually model the system. So we used, right, so in the beginning, Gary did, asked which of these graphs represent what happened, the relationships, the formulas. You can also take that one step further. Professor Spearman is fantastic together with Dr. Chu in this, right? And they help model what the, or basically help model the production system. So we use what's called a dynamic model. And what you can see here is you will see a simplified dynamic run of 7 designs running through the system. I'm just going to let it run, and you'll see what happens as a result. As I said, each row is a team, and every design is running through this production system. Now, I'll just pause it for a minute. So what you'll see is a design consists of different parts that different team members have to work on for their specific durations, okay? So here you can see the different parts of the design, or the task that has to be done, being given to each of the individual teams. And what that meant was that this model could not only tell us how long would it take for one design to go through the full production system, it could also tell us at what point do we start seeing bottlenecks emerge as we increase the number of designs. And then with that insight, we could also understand how long it would take the production system to complete all units depending on the frequency of starts we choose. Okay, so this was a science-based approach with data and assumptions that we could verify, that could allow us to model how long it would take the complete production system to complete all designs, which was a massively important insight, because this is very different from our typical Monte Carlo simulations, which are based on assumptions that are much harder to verify and don't really mean anything. Yeah. So with that, you could see where the bottlenecks emerge. These are the red dots. So we could see that in team 3, right, the number of tasks that had to be executed at a certain point in time meant that designs were starting to run into delays and were starting to end up in inventory. And that was a very important insight, because again, we could be much more targeted on what to address. So, as I said, the dynamic model was able to predict the total outcome. So when we looked at the project schedule and we had looked at the cumulative engineering process, the baseline schedule suggested, or was put, that they would complete all 30X designs in month number 30 from the time that they started. Through the dynamic model, we could show that based on their assumptions, their data, the projected output with their intended frequency of starts would put them back 5 months. And we would also see that there would be a constant backlog in engineering progress against plan. So they would always be, except for months 8 and 9, right? They would always be running behind. And that was an important insight for them. But what was more important is we could actually think, how do we optimize it? So because we now had a functioning model that was based on the actual production system that the team expressed they were using, we could look at how to optimize both the cycle time and the throughput. So we could optimize width, right? We could look at what is the optimum level of width to get the optimal cycle time across the units. We could also fine-tune the steps. So we could look at specific parts of the production system and choose to resequence, redesign. We could also choose to selectively adjust resource. So as you remember from our static analysis, and also from the dynamic model, we could see specifically which team needed an additional resource to get more throughput at an aggregate level. We could also, instead of adding resources, choose, instead of adding a resource, why don't we go into that operation or that set of operations and actually take out waste in the classic lean sense. And lastly, we looked at what kinds of mindset and behavior improvements could we do to ensure greater reliability when it comes to completing tasks as agreed. So those were some of the things that we had in mind. And so that's what we worked through with the product team. And then we got to the following, right? The model showed that if we would cap the width at less than they were doing, okay, and I've sanitized it, but effectively, we're reducing, I believe, the WIP by around 30 to 40% with what they thought they should have, or what they were planning to start, I should say. So by starting less, the model showed we would finish sooner. This was a super counterintuitive insight for the project team. We also looked at the longest chain of tasks in sequence, right? And we saw that one of the key things was the review times from the owner, okay? So what we showed to the contractor is that if they would be able to engage the owner on reducing their review times and the variability of their review times by 50%, that would help expedite the engineering phase of the project. So it would be in the owner team's own interest to try and improve their performance. And then we also looked at the effect of adding specific resource in the bottleneck teams. And we saw that the combined effect of a WIP cap, improving owner team review times, and the additional resources, according to the model, was actually sufficient to pull back the delay, right? So we had relatively minor tweaks that weren't too invasive for the team, actually showing a material performance benefit for the product as an aggregate. With that in mind, with that optimized, sorry?
2 minutes left for the wrap up.
All right, sorry, yeah. And so, with that in mind, we then started, hey, we now have a production system that shows we can finish on time. And that's when we switched to PPC to really drive the daily work and to ensure that that potential identified was actually captured. And that's how we then progressed the work. So overall, right, so PPM really brought tangible benefits. We mapped the standard engineering process for the 3 designs. We used the dynamic simulation model to identify the bottlenecks. We identified specific initiatives to optimize the process. We then established a weekly production control. We trained several clients in using that production control, and ultimately we de-risked the schedule by 5 months. And it was something that, was was a tremendous experience together with the folks from SPS. So I didn't manage. I hope I managed time. But,
yeah, thank you, Jan. So I appreciate it. So very, very interesting and compelling story, especially how you have used technology, the simulation engine that was built and the visual display in order for the project team to actually visualize the output of the application of PPM and how they can actually optimize it. Very, very impressive. We do have actually several questions here for you, and let's spend 5 minutes, the 5 minutes that we have left in your section, to go through them very quickly. The first one, let me see if I can combine a couple of them. So the question is, can you please elaborate more on the difference between the dynamic modeling you used and typical Monte Carlo simulations?
Yeah, and Roberto, you might have to help me here when you talk about Monte Carlo. But so the Monte Carlo is a simulation still based in deterministic is a deterministic basis in which we take a activity and try and estimate or try and put in some kind of plus minus duration. So it could be 20% longer, it could be 10% shorter. We take these guesses on what the difference of an activity is, and then we run this network, or like this, the Monte Carlos, and we run it 1,000 times, and then we look at the probabilities of how long a schedule takes. But the problem is that there's no actual basis for understanding that range, and it's also the events that get you off are not the ones that are inside the 2 sigma, but it's the tail events that mess things up. Okay, and this is where the Monte Carlo simulation falls short in helping truly understand how long it will take a project to complete. Right, and this is you take the opposite. You look at the production system approach, right, which is based on, and I don't know whether you've experienced it or to what extent, but it's These are scientific formulas based on actual measurable data. You can measure how long it takes a task. You can measure how long the variabilities of the task, and therefore science dictates how long it takes to produce the unit. There is no assumptions, there's no unverifiable assumptions in that. Yeah, and so it's what. Yeah, maybe.
One thing that I can follow in your request for me to jump in. It's important that what our audience understand is that what you were showing is not a schedule. What you were showing is a production process within a given system in an engineering, right? So the typical application of Monte Carlo simulation are on schedules, right? And there are several tools available in order to do that. But what you have done, Jan, for this particular challenge was to go to the production system, not to the schedule, and understand the throughput, the width, the reasons for playing with variability, and also use the science behind it, right? So there's another question. We can probably go for two questions. I'm going to combine these two questions because one refers to, what is the simulation tool that you used, and then also is what is the tool that was used for the visual, right? It seems that these individuals understand that they're two separate things. So I'll leave that with you.
So we use the production system optimization module from SPS. And Roberto, what's the official name, so I don't say it wrong?
It's a production system optimizer. Production optimizer.
Yeah, production optimizer, right? So we use production optimizer from SPS. And then, to be honest, the visualization that we made was actually made to, we took timestamps, which we can get, and you can read out, because again, at any given time, you can understand where your inventory is because it's based on the operational science and these formulas. So we took timestamps, and then we just asked our visual aids to visualize and model on the basis of these timestamps where our inventory was at any given time, and that's how they gave it back. So the visualization was purely to actually share the story of how inventory flows through the production system. That's
excellent.
Frankly
we have let's go for one more question. So there's one here that says, you mentioned the model predicted a 5-month schedule delay, which is great. And so this person is wondering why an approach like this is not used more often. Thoughts? So my thought on this is, it's a very good question. After we did this, right, for us it was an extremely powerful insight that we can actually baseline a expected project outcome on the basis of science and verifiable data. That was a tremendously impactful insight, and the ability to then take a model and make adjustments in a virtual environment before actually implementing it in practice, so that you can go through a lot more iterations to figure out how you really get to that optimized outcome. I think, I think the more people will see it and hear it, I think the more it'll be applied. I think it's an extremely powerful way to think through project execution. Excellent. Thank you so much, Jan, for
it should be used more.
Thank you so much for you answering the questions, and thanks for joining us today. I mean, the results that you have and the approach actually that you have shown us and how you have done it it's quite important and interesting. I personally like, again, the way the display worked out and how you and your team did it. So very, very nice. Conscious of time, we need to transition. Thank you so much, Jan. We need to transition. Thank you.